All right, welcome back after lunch. So I hope you're ready for the last talk of our meeting. And the talk will be about by Joy Monteiro, and we will hear about energetics of heat waves and analyzed models using Reynolds decomposition.
Thanks, Manita. Tim is not here, but I want to thank him for inviting me. Clearly not the kind of waves we were talking about for the past 2 weeks. More like a wave of relief when this whole session is over. I think this is more akin that wave. I'm just going to try and keep the talk fairly straightforward because this is work that we are currently doing. I would really like any inputs that you may have. I think it will be helpful in reflecting about the results that we have. Yeah, so this work was mainly done by Abel, who's a master's student. So the results that Abel got for his master's thesis were fairly hard to interpret. So he spent another year working on this, and now he has to also work on his master's work. It's been interesting, and I hope you find it interesting too. And one slide here is also something that Hardik, who's working with us as a PhD student, he's been doing. I'll talk about that later. So I just want to motivate the talk and try and explain where we are coming from. So this is a figure from a very recent review on the mechanisms that drive heat waves. And you see that this is a very classic picture, reinforced by a lot of studies, in the sense that you have a strong anticyclone, which is called a block. So everybody understands what a block is, but finds it very hard to define what a block is, which leads to some of the difficulties in this literature, especially the dynamics part. And so you have a block, which means that you have subsidence, you don't have any clouds, and therefore you have increased sunlight reaching the surface. And that sunlight is absorbed by the surface, and which increases the heat transfer from the surface to the atmosphere. This can happen in two ways, and when it happens primarily through sensible heat fluxes, which is not related to evaporation. I mean, let's say the surface is dry, then you tend to sort of enhance the heating close to the surface. What I would like to point out is a lot of this picture, I mean, quite literally, if you see most of the arrows are going up and down, it is mostly a one-dimensional picture of heat waves. And it's a very, I mean, it's primarily a diabatic picture of heat waves. So you have solar radiation, you have sensible heat fluxes. So the main role that dynamics plays here is to create this anticyclone. So if you can get an anticyclone, then it's all diabatic, it's all one-dimensional. Let's say you want to understand what controls heat wave characteristics, right? So typically you want to know, let's say, the duration of a heat wave, what controls the duration or what controls the intensity. Then you say, okay, the way to make a heat wave longer is to make this block go on and on, right? So one way to do that may be to have some sort of increased subsidence because you have deep convection and rainfall elsewhere, or if it is forced by a stationary Rossby wave pattern, something that can keep the anticyclone going. And if you say you want to make it more intense, in this framework, the way to make it intense is to desiccate the surface. So you make the surface dry, therefore less of the heat is exchanged as latent heat fluxes and more as sensible heat fluxes. And therefore you tend to generate a large amount of heat very close to the, or maintain more heat close to the surface. So there is this small little part all the way in the corner, which is what dynamicists would be probably also interested in, but what has been observed, especially for mid-latitude European heat waves, has been that this particular term, the advection of heat, is supposed to be negligible, and the primary controls on heat waves are due to these. I will return back to that statement a little later, because like I said, this is a mid-latitude sort of a statement. So, like I said, a lot of the dynamics here is about the blocking, but that's no fun for dynamicists. And maybe we can see what else we can learn about heat waves by getting rid of that, and getting rid of that, and getting rid of that. So get rid of all the primary drivers that are identified to be important, and then see what controls heat waves in the model. So this sort of are the questions that I hope to at least discuss, if not answer fully, is that what role does adiabatic advection play? And is it only influential along local temperature gradients? Because this is very clear, right? So you're advecting warmer air, and that's what creates a heat wave. And if you look at climatological gradients of, let's say, dry static energy, it's mostly equator to pole, so that's the primary gradient. So it sort of reasons, I mean, the reasoning will go that when you want to talk about heat waves and advection in heat waves, you're primarily talking about equator to pole advection. So for instance, when people talk about heat waves in Europe, it is advection from North Africa. That is important. Another question we want to ask is that the only influential component that we should worry about? So in so to speak, the V prime advection term. And does advection play any role in controlling heat wave characteristics? And does this influence depend on the location where you live? So to sort of get to the answering these questions, we had to design a GCM experiment. We designed it using CLIMT. CLIMT is a modeling package that we develop ourselves, especially for the students out here. If you want to do simplified atmospheric modeling, CLIMT is a very nice tool. You can write your whole model in Python and run it. So do play around with it. So this is how we set up the model. So it's gray gas. So we don't care about radiative effects of water vapor, for example. And I haven't mentioned here, but the solar forcing is constant, so we get rid of that. We have a boundary layer. We have a surface that is thermally energetically consistent. We don't have clouds, so anticyclones and dissipation of clouds doesn't play a role. There's no diurnal cycle. There's no seasons. It's a fairly coarse resolution model, but has sufficient vertical resolution. And we run it for 1,000 years. And it is simple, so you can run it for a long time. And I'm sorry, it's not very obvious here, but we studied heat waves in 4 boxes, which span, which are 10 cross 10 boxes from 55 to 40, the northern edge. And this is the surface plot. And as you can see, the climatological gradient of temperature is equator to pole, the primary gradient. There is no zonal asymmetry in the model either. You have a sort of low thermal capacity layer here, which acts as a proxy for land, and the rest of it is ocean. And we set it up in such a way that we are just entering into the summer in the northern hemisphere. So you can see that the northern subtropical jet is becoming weaker, and you have a winter-like jet in the southern hemisphere. So, I mean, typically we define heat waves as some sort of temperature anomaly that exceeds some percentile. which is great for actual measurements. But when you're working, I mean, for a dynamicist, it's a problem because surface temperatures are strongly controlled by literally the surface. And therefore, how do you bring in a role for the circulation itself? So what we instead did was try and look at some part of the lower troposphere, surface to 850 HPA, and we saw that you had a really good correlation. So instead of trying to look at the surface temperature, we try and look at the dry static energy budget in the lower troposphere. Then hopefully, then you can get some of the influences of circulation itself. And therefore, we can do our analysis on a conserved variable rather than temperature, which again is a problem. And very quickly, this is the mean sensible heat flux during a heat wave in this model. And you see that it is negative. Negative means there's a reduction in sensible heat flux, which in this model means that the atmosphere is warmer than the surface at that point in time. And therefore, you're not delivering energy from the surface to the atmosphere, but the other way around. And which is nice because we wanted to eliminate another boundary effect as well. So now we are saying if you have a heat wave, it's mainly due to advection. And that's something we also validated. I don't have a slide for that, but that lower layer dry static energy changes is primarily due to horizontal fluxes. So now that we've set up a model carefully, now we want to look at the heat waves in this model. And these are all the heat waves that were generated for a particular land location. And then we start looking at particular classes of heat waves themselves. So really intense heat waves, for example, or really long heat waves. There are some which fall in both categories, they get double counted, but that's really not an issue for what we're doing now. So there's a whole bunch here. Most heat waves really lie here. And what we want to do is compare really intense versus the really low intensity ones, or the really long ones versus the really short ones, and try and see, can we understand something about what's controlling these heat wave characteristics. And this is just how these heat wave characteristics look across the boxes that I mentioned. So as you go, so one box is almost entirely in the westerlies, surface westerlies. And the final box is almost in this region. So there's really no mean winds. And that's something we want to, I mean, that was by design. And you see that the intensity drops very systematically as you go from the one which is closest to the jet to the one that's away from the jet. And the duration rises systematically. And that's only for the 90th percentile. The 10th percentile seems to remain flat. We don't yet have an answer for this, but this is where things stand. And so, okay, now shall we, now we want to look at the life cycle. Why is it that a heat wave is intense? And why is it that a heat wave is long? And looking at the dry static energy budget, can we get some insight into why that should be? So these are the 4 boxes that we have. No, I've just taken 2 of them, the most extreme ones, the most poleward and most equatorward. And you see that, okay, if you have a high intensity heat wave, it seems to start off with very high DSE flux. So you're essentially pumping in a lot of energy into that lower tropospheric box. And over time, and in a very almost linear fashion, it drops and then it starts cooling. So your peak of the heat wave will likely be somewhere here, and then the heat wave dissipates, and then you're more or less back to the regular situation. And the time fraction we have used instead of time actually, simply because it's hard to compare across duration and intensity otherwise. Whereas if you look at high intensity heat waves, so you start off with a nice kick to your DSE budget. It drops fairly rapidly, but then nothing really happens. So it sort of is in a constant forcing state for a very long time, and then it very dramatically drops. So there's a very clear difference between the signature in terms of DSC fluxes for very intense heat waves and very long heat waves. The reason they are long appears to be that even though in the initial parts they behave like intense heat waves, they ramp up quickly, they ramp down quickly, but in between nothing seems to change, and that's really key. And if you look at the equator Morse box, it's the same. It's just that the amplitudes are much lower. I would say, yeah, are lower for both high intensity and high duration. We'll not worry about this so much because, well, they're not as interesting for now. The signature seems almost the same, it's just a little less in amplitude. And that seems to also explain why you have a decrease in intensity. So you generally have a lower DSC forcing in the model. So just to summarize, the high intensity life cycle looks like the low duration. High duration looks like low intensity. But this is just as an aside. What is interesting is that high intensity heat waves are almost linearly go down to zero and go to the negative, whereas high duration heat waves ramp up quickly, then nothing really happens, and then they ramp down quickly. Now, what we wanted to look at was, okay, is this primarily due to meridional fluxes? And this is just the Reynolds decomposed components. So you don't have a horizontal gradient of climatological dry static energy, so that term doesn't come up. The climatological meridional winds are negligible, so that doesn't come up. So you only have 4 components, which are meridional advection of climatological DSC, meridional advection of anomalous DSC, which are shown here. And you see that regardless of which box you choose, the amount of energy that is fluxed in by the meridional component, which is just carrying the climatological gradient in, tends to be fairly similar. It's 0.6, roughly around 0.6 into 10 to the power of 19 joules per day. So they do have some shape over the life cycle, but it's all above zero. So the meridional, if I were to call this eddy mean, where the first term talks about the wind and the second term talks about the DSC. So the eddy wind is, or the eddy mean is mostly positive, whereas the eddy is mostly negative in the meridional direction. So this mostly heats and this mostly cools. And what is really interesting is the zonal term. So this is mean winds advecting the anomalous DSC. So because it's mean wind, it's it's just a constant. So you're essentially just translating a DSC anomaly, right? So that has a signature which looks very similar to what you saw here. In the sense it starts off in a positive value and then decreases to a negative value. And that's true for the boxes which are close to where you have surface westerlies, and then it just goes to zero for obvious reasons because there is no climatological mean value there at all. This almost, and the same picture also holds for the long heat waves. And if you see that it's quite noisy and there's a lot of spread in the meridional components, and the only term that really gives a very coherent signal is the zonal advection term, even though the climatological gradient is in the meridional direction. I'm going to skip this because I don't have time, but so this is sort of summarizing what we're saying, that the eddy mean contributes only to accumulation, eddy contributes only to ventilation of DSC, and the amplitudes are really not sensitive to the location where you're looking at the heat waves. On the other hand, the zonal term seems to be very important. It's negligible away from the jet, especially the mean eddy term. And this amounts to just a pure translation of the DSC anomaly. And the eddy terms become negligible close to the jet. So, okay, we have this sort of a picture where we are saying that, you know what, there are these meridional terms, but they seem to provide more or less a constant heating or cooling. So if you want to create an intense heat wave or a long heat wave, you should not be looking at the meridional terms, but you should be looking at the zonal terms, which is sort of very counterintuitive. So where does it potentially be useful? So if you look at South Asia, you have fairly low soil moisture because we have a very strongly seasonal rainfall pattern, and therefore it's really dry in the heat wave season here. And we also have very little cloudiness. So it's not like if you put an anticyclone, you're suddenly going to remove clouds and therefore you have strong solar heating. You always have strong solar heating, right? So this sort of a picture, though we initially said we just want to get rid of them, it actually has some utility, especially when you look at heat waves away from the mid-latitudes. And we did a similar analysis for temperature variability in this box. It's slightly different because we are not just looking at heat waves, but also at general, any delta T which is positive. And we looked at different months. What we wanted to see was, do the different components contribute differently? And in fact, as you move to June, which means as the jet moves away from the location of interest, you see that the contribution of the eddy zonal term actually increases. I mean, there's a nuance here in the sense that the vertical component and the meridional component are linked because of the quasi-geostrophic omega equation, because it's mostly balanced flow that is causing these temperature anomalies. But what we wanted to just bring out that despite the fact that there is all this complexity in the real world, we do see some of these effects of the circulation in data. Right, so I'll just wrap up here. I'm sorry, I'm a little over time. I mean, there is a case to be made that heat waves actually exist in a turbulent fluid, and therefore there's likely going to be advection and chaotic advection, and we can move beyond a single sort of one-dimensional view. And that meridional advection, though it has been always said that it's probably the most important component, it plays a very different role. It mainly acts as a forcing or a cooling, whereas it doesn't play much role in determining the life cycle of heat waves. What's really interesting is that the zonal advection plays an important role in shaping these life cycle characteristics. Since close to the jet, this is just translation, pure translation. What really matters is the geometry or the shape of the DSC anomaly that is being translated. So the gradient of that anomaly is what's going to give you an intense heat wave, or it's going to give you a long heat wave. So I mean, it's sort of, the word I like to use, it looks like a conveyor belt. So you just drop some DSC anomaly and the conveyor belt just moves it across your area, right? And as that passes by you, you're going to see a heat wave that is rising and cooling. So yeah, so that's it. Thanks for listening.
Thank you, Joy. Questions? Actually, I had a question,
sure.
Just out of curiosity. So do you think you could use some of, is there any relation between this and the marine heat waves, probably?
I mean, that is something we actually want to test in the sense that the simplest model for a marine heat wave is just a stochastic model. And you just force it using some noise term, and you assume that the noise has a particular distribution. Now, I mean, one thing I would like to understand is whether specifying the probability density function of that noise term would play a role, because again, different parts of the atmospheric flow will have different kinds of effects. And you know that when you have atmospheric heat wave sitting on top of a marine heat wave, you're likely to have a different sort of an impact rather than a climatological.
So more from a GFT perspective, so we have different kinds of geophysical turbulence. So when you put in these heat waves, what kind of turbulence statistics do you think would be affected by heat waves? From these idealized geophysical turbulence theories, once you start identifying heat waves, what are the variables that would change?
In a sense, heat waves are part of this turbulence, right? So they're just extrema of this turbulence. So if I'm not able to get the question, so we are not going to put heat waves. Heat waves exist.
Right. So I guess what kind of models would predict these extreme events very well?
Just in terms of statistical model, you mean?
No, spatio-temporal structure.
Spatio-temporal
something as simple as QG might not have a lot of these details, right? So what more would you need?
I mean, actually, Hardik, who's working with data, shows that at least in times when you're close to the jet, a lot of this can be explained by QG. So you essentially have a relationship between vertical velocities and the balanced flow, which is a quasi-geostrophic omega equation. And a lot of the you can see that he observed that the vertical advection term was important, and a lot of this W prime is essentially quasi-geostrophic. So yes.
So the scales do not necessarily correspond to mesoscales in the atmosphere?
No. In fact, most heat waves are balanced in that sense.
Okay.
It's balanced, but it's not mesoscales. What would you mean by what kind of motions would this
I'm
be?
sorry, in the atmosphere, unbalanced is mesoscale. In the oceans,
okay, so it's an optic scale.
Yeah, so it's a terminology issue.
Okay, okay. More questions? Pascal? Okay, well, then thank you, Joy.
Thanks.
You can